This video will showcase bitwise operators being used in very cool ways. So this first program will swap two numbers by reading them from input, swapping them, and then writing them to output. If I type in the numbers 116, you can see I get 16 and 100. It makes use of the XOR operator, which if you apply it twice using the same number, you'll get your original number back. You may feel free to pause and verify that this is the case with the truth table. So I've written in comments what's happening in each of the lines, but essentially we're applying the XOR operator and undoing it to get back the number that we want. This next program will calculate the floor of the logarithm base 2 of a number, and it makes use of the floating point representation. So here you can see that a floating point representation contains its sign, the exponent, the only thing which we care about in this case, and the mantissa. What we can do is that first, if we assume our number is a positive integer, there's ways to extend the case for negative integers, and then convert it to its floating point representation, we'll get this binary representation over here. Now, if we treat this like an actual binary number and do some bit shifting with it, we can get the exponent, which is stored in the sequence of bits. Then we subtract 127 to get the actual exponent. So if we test out the number 16, this should give us 4, because 16 is 2 to the power of 4, but 15 should only give us 3. Our final program makes one very small change to our previous program in order to calculate something very different. So this program will calculate the number of consecutive 0 bits on the right side of a number's binary representation. What we can do is, again, scan in the number and do this operation here, where we apply the AND operator to a number and it's negative. So this makes use of the 2's complement representation of a number, which is the most common representation of negative numbers used in operating systems. And you can see here that the 2's complement is calculated by swapping every bit to the left of the last one and keeping all of the bits, including the last one and to the right of it, the same. So if we apply the AND operator between these two numbers, all of these bits here should go to 0 because we're applying the AND operator to two different bits, and all of these should be kept the same. This means our output of calculating A and negative A will be 1 with the number of consecutive right 0 bits appended right afterwards. Now we can just calculate the logarithm using the trick before, which we can see here and here. And if we run this program, if we type in 16, because it's 1 with 4 zeros afterwards, we should get 4. But 15 should give 0 because it's an odd number. And we can also test 12, which should give us 2.